Okay, so we'll start the next session in this course on artificial intelligence. So we were talking about heuristic search which is memory bounded. So you also have, like I said, we spoke about the RBFS and the IDA star algorithms. So we'll now talk about the memory bounded A star and the simplified memory A star. So what is done here is that you have some limited number of nodes. Okay, so suppose you have a tree where only 3 nodes or 4 nodes are available. What you do is that you proceed just like A star and you go along expand the west leaf and keep going that way. But once you find that the memory is over, okay, so what you do is that the subtree, you actually remove a whole subtree. Okay, so if you find that the subtree has f value which is say slightly higher, you are going to remove it. But as you go down one tree, if you find that the f cost of the forgotten subtree is better than what you are doing now, then you note down at the root node the f value for this path which you are now working on, and you expand the other subtree, and you keep doing this at every point in time. Okay, so you are removing subtrees which are worse, but if they get better than what you are using now, then you are going to go back to those because you will have stored that information of the f value along the forgotten subtrees. So if you keep doing this, even with the small memory, it's possible for you to get a solution. The only thing is that if you have a solution say at depth d, you should have at least d nodes available to you. If you don't have at least d nodes available to you, you will not be able to get a solution by using this method basically. So what I want to basically do is show you for a particular problem how the A star algorithm actually works. So let us consider okay, so suppose we start with the 8 puzzle. So we have the 8 puzzle here. So this is your start node. And the goal state that you want is basically 1, 2, 3, 4, 5, 6, 7, 8. So if we consider this as your start state, there are 3 possible ways you can move this blank. Okay, it can be either moved this way, or it can be moved this way, or it can be moved that way. So you have 3 branches that you will get when you expand this. So the first one would be if you are moving the blank to this side, so you will get 2, 8, 3, 1, 6, 4, 7, 5. And the second one would be 2, 8, 3, 1, 6, 4, if you move the blank to this side. And if you move the blank up, so for that you will get 2, 8, 3, 1, 4, 7, 6, 5. Okay, so these are the 3 possible nodes that you will get when you expand the start state. So in the case of breadth first search, what would we do? We would then expand this node, expand this node, expand. So here there's only one way of expanding this, right. So you are going to get 283, you move the blank up, okay, and this again there is only one way of doing this, okay. So you will get and this one there are three ways, right. So you will get 3 nodes from this, okay. So if you move the blank to the top, you will get 2, 3, 1, 8, 4, 7, 6, 5, and here if you move it to the left, you will get 2, 8, 3, 1, 4, 7, 6, 5, or if you move it to the right, you will get 2, 8, 3, 1, 4, 7, 6, 5, right. So this is the breadth first search we are doing here. But suppose we take only one node at a time, okay, so we come this way and then we come this way, and then this can be done in 2 ways. So you will get 2 nodes like this, okay, and then we go down like this till we reach the end point, okay. In other words, there is no more nodes to expand, or you get the goal state, right. And suppose you get no more nodes to expand, you have to backtrack and you have to take another expansion and continue from there, okay. So that will give you your depth first search. So let us look at the ordered search, okay. So what we need to do is we need to use a heuristic over here. What would be the heuristic that we can use? Okay, so we want to use f of n is equal to g of n plus h of n, okay. So let the g of n be equal to the path length, okay. In other words, all these have path length of 1 and these have path length of 2, etc. And h of n would be the number of misplaced tiles, okay. So if we take here 2 is misplaced, 8 is misplaced, 7 is misplaced, okay. 1 is misplaced, 6 is misplaced, right. So if you see the number of misplaced tiles here, 2 is misplaced, 8 is misplaced, 6 is misplaced, 7 is misplaced, 1 is misplaced. So this would have a value of 5, right. Then if we come to this, the f value will be equal to 1 plus number of misplaced tiles, because 1 is for g of n, right. So this has a value of 5, okay. So if we actually expand and put the values, you are going to get 6 here, 6 here and 4 here, okay. Now obviously you will choose the one with the lower cost value. So you are choosing this and you are going to expand this and you are not going to expand these. So these have a value of 5, 5 and 6, okay. So you are going to choose one of these and expand, okay. So suppose you decide to expand this one, right. You will get 2, 3, 1, 8, 4, 7, 6, 5, and you get 2, 3 this way, 1, 8, 4, 7, 6, 5. Okay, so this has a value of 5 and this has a value of 7. Then you are going to choose the 5. So you expand this, right? So you are getting here 2, 3. So what happens is finally you are going to expand this and you are going to get your solution here, okay. So this is how the A star algorithm basically works. And one thing you can notice is that and actually this is 4. So you find that the value of f of n actually keeps increasing as you go down. It either increases or remains the same. Okay, it does not decrease at any point in time. So that's what is known as the monotonicity here. Okay. So the next thing that we are going to talk about is how do we design a heuristic function. Okay, so we need to know how to design a heuristic function for the problem that we are looking at, okay, because the heuristic function is very important, and if the heuristic function is wrong, you are going to get wrong results. Okay, so what we will look at is the 8 puzzle basically. Okay, let us look at the 8 puzzle first and try to find different heuristics for it basically. Okay. So like I said, like we did there, it could be the number of misplaced tiles. Okay, so if we take H1 as one of the heuristics that I used, H1 gives the number of misplaced tiles. Okay, so if we look at this figure over here, okay, how many tiles are misplaced in your start state as compared to your goal state? Okay. So 1, 2 is misplaced, 5 is misplaced, 8 is misplaced, all of them are misplaced basically, right? So what do you find? It has a H value of 8, okay. Now the second heuristic that you can basically use is by how much is it misplaced? In other words, how many spaces should you move to come to the actual position. Okay, and since you are not able to move in a diagonal way, we only consider either up and down or left and right. So if we take something like say 1, okay, so 1 is here and 1 is there in the goal. So between the goal and the 1 here, there are 3 possible moves, 3 moves that will have to be made, and you have to do that for everything. Okay, so for 1 it is 3 possible moves. If we take 2, it's 1 move, right? You need to make 1 move. If you take 3, then there are 2 moves, right? So if you keep adding these up, it gives you the second heuristic. Okay, and the actual solution is 26 steps long, right? So what you find is that if you take this H1 or H2, they do not estimate the true solution cost basically. Okay. Now how do we evaluate the heuristic that we are using? So for example, if I have a heuristic H1 and I have a heuristic H2. So how do I see which is a better heuristic? So there are 2 ways of doing it. The first one is to see if you look at the tree that you have, what are the total number of nodes that are generated by the A star algorithm. Okay, and suppose it goes to a solution depth D, we use what is called the effective branching factor. Okay, so that is something like an average branching factor. So suppose I have n nodes in the tree. Okay, so n plus 1 is equal to 1, which is the root node, plus B star, if you take B star as your effective branching factor and B star squared etc. into plus B star to the power of D. So, you find what is B star over here, right? We know D. So, suppose A star finds a solution at depth 5 using 52 nodes, okay. So, you can put 52 here and you can put your depth to be equal to 5 and you can find the effective branching factor B, okay. So, you find it's has a value of 1.92, okay. So, the effective branching factor, it varies, okay, depending on the problem instance that you have used, okay, but value which is closer to 1 is a better effective branching factor, right. So, if we take the heuristics H1 and H2, okay, so we have what was done here. So, you have three methods. One is the iterative deepening search, okay, and A star with heuristic H1 and heuristic H2 were done, okay, and different you know a lot of experimentation was done at different depths, right, and these are the solution. This is a solution that was got, okay. So, if we look at the effective branching factor, we can see that A star is doing better than the iterative deepening, and over there the smaller effective branching factor is better, and we can see that the H2 is doing better than H1, and this one actually gives the number of nodes that were expanded. So, you can see again H2 is doing better than H1 and that is doing better than the iterative deepening A star. So, we can say that H2 is a better heuristic than H1, okay, by looking at these results that we have, right. Okay. So, what happens is that even for small problems with D is equal to 12, A star with H2 is 50,000 times more efficient than uninformed iterative deepening, and H2 is always better than H1 if we look at this particular experiment which was carried out. So, what can we say about this? We can say H2 dominates H1, okay. In other words, heuristic H2 is greater than the heuristic H1. So, H2 expands fewer nodes as compared to H1. So, in other words, it takes less time to come up with a solution than H1. So, what we need is, if you have a number of admissible heuristics, say H1, H2, H3, H4, we need the maximum of those, okay. So, we need the heuristic which dominates all the other heuristics basically. So, it is better to get a H2 which is higher, just like H2 is greater than H1, right. Okay, so there must be some methods of coming up with the solutions we are talking about. So, how do we come up with these? So, generally one method of doing this is to reduce the restrictions on the problem. So, you come up with a solution to the relaxed problem and use it as a heuristic, okay. So, what you are doing basically is that, for example, when we say that you are looking for the straight line distance between the node N and the goal node, you are reducing the restriction that it has to go along the roads, right, and because of that you are using the relaxed problem to come up with the heuristic. So, what happens is that the state space graph of the relaxed problem is a super graph of the original state space, because when you remove the restrictions you have more added edges to it, right. And because you are removing some restrictions, you find that it will be a consistent solution basically, okay. Just like when we take the straight line distance, it is smaller than the actual distance. It's less than the actual distance from a node to the goal state. Okay. So when we take a relaxed problem, you are going to get a heuristic which is admissible, consistent, all those things, right? So that is one way of finding the heuristic, right? So if we take in the 8 puzzle, okay, so what we have is that a tile can move from square A to square B if these are the conditions that we have. A is horizontal or vertically adjacent to B and B is blank, okay. So we can generate relaxed problems by removing these conditions, okay. A tile can move from square A to square B if A is adjacent to B and we have removed this B is blank, okay. So that is one condition removed. A tile can move from square A to square B if B is blank, okay. So we have removed that first condition there. A tile can move from square A to square B. We have removed both the conditions, right. So what we are doing here is actually getting conditions, getting the relaxed problem and finding the solution for that and using that as the heuristic, okay. So like it says from A you can derive H2, okay, and from C we can derive H1, okay. So that is one way of getting the relaxed heuristic. Okay, so you have people who have actually automated finding the heuristics and you have a problem called absolver which actually generates heuristic automatically from problem definition by finding the solution to the relaxed problems and other such techniques, right. Now what happens is that you will find that a number of heuristics are possible for one problem. For just for example, in the 8 puzzle, we found two heuristics H1 and H2. So suppose there are n such heuristics H1, H2, H3, Hm, right? So which is the heuristic to use? We need to find the maximum of all these heuristics, okay? And that is the heuristic which needs to be used. And this heuristic will be admissible and it will be consistent and it dominates all the other heuristics that you have, okay. So that is the heuristic that we need to use over here. You can also derive heuristics by finding a solution to the sub problem, okay. For example, if we look at this figure here, we have actually created a sub problem from the problem where we say that we consider only 1, 2, 3 and 4. Okay, so this is the original start space 1, 2, 3 and 4 and this is the final 1, 2, 3, 4 that we need to have. So how do we find a heuristic for moving from this to this? So we can create two sub problems here, one for moving 1, 2, 3, 4, another for using only the rest of them, okay, 5, 6, 7, 8, etc. So if you divide it into sub problems and then use those sub problems to find the overall heuristic, okay, that is one method of actually finding the heuristic, okay. So this is what is called the pattern databases, okay. So these pattern databases are used to store exact solutions for the sub problems, okay, because the sub problems obviously are smaller than the overall problem. So you can store exact solution costs over there, okay. And one overall problem can be divided into 2 or 3 sub problems and you can use the solution to these sub problems which are already available to you and make use of it to get the overall heuristic, to get the overall problem. So this is one way of getting the heuristic. It could have been 1, 2, 3, 4, it could have been 5, 6, 7, 8, 2, 4, 6, 8, you could use any type of thing like that. So what you basically find is a combined heuristic of this kind is much more accurate, okay. and the number of nodes generated when solving random 15 puzzles can be reduced by a factor of 1000. So we can see that 8 puzzle is not so complex, but if we look at the 15 puzzle, so that is a 4 by 4, okay, 4 by 4 grid, or if we look at a 5 by 5 board, so that's a 24 puzzle, then it gets more complex, and using all these things actually helps you to get solutions much faster. So it's possible to solve random 15 puzzles in a few milliseconds, and the number of nodes generated is reduced by a factor of 10,000. Okay, so and in the case of 24 puzzle, a speed up of a factor of 1,000,000 can be obtained. Okay, so that's a lot if you are able to use these disjoint pattern databases. It can be done. It's good to use it, right? Okay, another is that you can learn from experience. Okay, so what you do is you run lot of 8 puzzles, and from these 8 puzzles you see what is the experience that you have. Okay, so when you find optimal solution to the 8 puzzle, it provides examples from which the HN can be learnt. Okay, a learning algorithm can be used to construct a function that predicts the solution costs. So what you do basically here is you have a number of features to your problem. Okay, for example, in the case of H1, the feature we used is number of misplaced tiles, right, and in the second case we used another feature, right, or you could use more than one feature. You can have 2 or 3 feature, or you can have 4 features, etc. Okay, and then what you do is you generate a number of randomly generated 8 puzzle configuration, and you gather statistics from that, and you use those statistics. We might find that when x1 n is 5, the average solution cost is around 14, and so on. In other words, it takes like a path length of 14 to get the solution when your x1 n is 5, etc. So you can use information like this, right? So suppose we have heuristics, we have features x1, x2, etc. Okay, let's consider just 2 features, x1 and x2. So if you have 2 features, x1 and x2, you can combine those 2 features by using weights or constants c1 and c2. So we can say h of n is equal to c1 x1 plus c2 x2. Okay, and by running it a number of times, you can find out what is the value of c1 and c2 that you need to use. Okay, so that way you can develop a heuristic over there. So these are all the different methods which we can use to get the heuristics. So we'll stop at this point, and the next session will be on game playing, so which is again a search tree for finding the solution, but there is a little more complication involved there because you also have an opponent. So we'll talk about that in the next session.